So, beginning a review. One thing you might notice that I posted the homework and then I decided to change it. That last problem, I'm pretty sure I did it right, but it didn't feel very comfortable to me. And I really should have made it something like quarks, because, you know, a proton is 3 quarks. And they have their fermions as well. But I just changed it so you are just finding the spin state if you have a 1 spin with a 1/2 spin combined. And so you should have a quadruplet and a doublet. So, and I went from a 40-point problem to a 10-point problem because it got much easier. All right. Reviewing for the exam. The first stuff we had, the stuff for the first exam. So what I have here is just basic review, and then we'll look at the first exam to make sure we could go through and understand, do those questions again. Okay. So the origins of quantum mechanics, remember that we talked about Schrodinger giving a talk about de Broglie's idea that you have a wavelength for particles. And then I can't remember who it was that said, well, if that's the case, shouldn't there be a wave equation? And he went down and he found a wave equation based on energy balance. The kinetic energy plus potential energy is total energy. The Hamiltonian is the name for that energy, the kinetic energy plus potential energy operator, because it's based on Hamiltonian dynamics. And so that's where we get the wave method for quantum mechanics. And probably, what, 70, 80% of what we've done has been wave method of quantum mechanics. So of the 2 methods, the wave one is the one we talked about the most, although we've ended with a lot of the matrix method. Wow. I didn't do it. There we go.
Yeah, it's been really touchy the last hour or so.
Now, in quantum mechanics, we had some new ideas, unless your math is already to this level of sophistication. So I, of course, just look at Christopher and say, well, his math is probably more sophisticated than mine. So you have operators, mathematical functions that act on other mathematical functions. And some of them, the function is very simple. It's a constant. It's just multiplicative. Some of them were more complex. You saw differential operators. And we did some tedious work with integral operators to show that they can exist. And those operators correspond to observables. Observable is the important thing. That's where the rubber meets the road. That's where you make a prediction that you can test. So you can predict, okay, if I take 5,000 measurements for the position of a particle in the box, wow, really? If I take 5,000 measurements for the position of a particle in the box, the average will be my expectation value. And so I calculate what the expectation value is, compare it to the average. If it's not, then I know I have a problem, right? My quantum physics is not making correct predictions. What reason do we have to believe quantum physics to begin with? Because it makes correct predictions. So if it doesn't, well, we got a problem with that fundamental basic piece. So we have the operators corresponding with observables. And then we have a term here. In retrospect, these things make a lot more sense than they did when we started, I'm hoping. You know, so the eigenvalues, now that we've clearly defined what eigenvalues are, well, let me ask you, what is an eigenvalue?
It's like what you get after you operate on the side, like the wave functions. So like it's
okay. That is a correct statement. Here is a good way of writing the relationship that you articulated in words. The operator acting on a specific state. What do we call that specific state? Okay, the eigenvector or eigenstate. Either one works. I'm differentiating that from wave function simply because wave function is more general. right? If I just put psi, I'd say that's my wave function. If I put psi sub n, yes, that's my wave function, but it's one of the specific states it can be in. And so that's why I'm using different verbiage there. Is equal to the eigenvalue for that state, so it's an E sub n times psi n. So eigenvalue times the eigenstate. Therein is the specific I was looking for that you didn't say. It is one of these, an eigenvalue is one of the specific values you can get. Right, so if you're in state n, you get eigenvalue n, E sub n. If you're in state m, you get eigenvalue E sub m. So it's one of the specific values you can have. There is really something wrong with your room. Hey, but at least it's coming only about once every 3 minutes. Well, 2 minutes.
I get some work out.
Yeah, we'll time it next time. I'm going to do that. Next time it goes black, I'm going to look at the clock. Okay, so we have the eigenvalue defined there with the eigenrelationship. It's an important thing. Now I'm going to jump forward actually to stuff that I think was on test 2. Or maybe it was test 3. The space that our solutions fall in quantum physics. What do we call that space? Our operators are Hermitian. Operators have to be Hermitian. It starts with H still. Starts. That's right. That's right. Your eigenvectors form a Hilbert space. And that Hilbert space is a space that supports the inner product. And it has to be a complete set of eigenvectors available, which means that you can describe any function in that Hilbert space as a linear combination of each of the eigenvectors. So the inner product, the dot product is an inner product. We have in quantum physics that's the inner product. That's equivalent to a dot product in Euclidean space. What's the dimensionality of Hilbert spaces? You know what we say in physics class usually? N. In an n-dimensional Hilbert space, it depends on your problem. In virtually every problem we've done, it's been infinite. You know, particle in the box, there was no upper cap on the n values. Hydrogen atom, there's no upper cap on the n values. You know, we've been working in infinite Hilbert spaces. Then again, for the electron spin, it was finite. And for that matter, we didn't have a function we could write for the electron spin. Last thing on the slide that's super important, quantum mechanics is probabilistic. What did Einstein say about this?
Said that we just don't have all the information. That can't actually be bubbles.
Einstein did not like this idea at all. He said that God doesn't play dice with the universe, that it's got to be that we just don't have the information, what you exactly said. The conventional understanding right now is that Einstein was wrong. That nature is fundamentally probabilistic, not deterministic. Fundamentally, if we knew every darn thing about you, we still couldn't determine your next decision. Now that here we're talking about human decision making, it's easier to understand, yeah, quantum physics is kind of like that. I could know everything about Chris. I'm still not going to know, what decision he's going to make next. Can't tell you which shirt he's going to choose tomorrow morning. And unless I knew everything about Chris and knew that he only had one style of shirt with 700 of the same thing or something. But Yes. Well, I don't either. I pick shirts randomly. My wife tells me this morning, "What? You're wearing a long sleeve shirt? It's going to be warm today. Why do you wear a long sleeve shirt on a warm day?" I don't think about it. I just grab a shirt. That to her, just for the record, makes no sense. Maybe your wives will be different, but yeah, to her, that makes no sense to not pay attention to the weather when you choose your clothes. Statistics. So we had to learn to do some statistics. We had to find the expectation value. We had to find the standard deviation and the most probable values. So let's get to the test. Yeah, 13 minutes. Look, the lights haven't gone off. Maybe it's because you've been opening and closing your book. I don't know. But that's the longest we've had. So let's just look at these questions. You've had them all. Describe what expectation value means. I think you both did not get that right. So let's see if you have it right now. What's the expectation value?
It's like the average of
Let me say of a statistically meaningful number of measurements. And how do you calculate that? Yeah, d whatever. I put dx, and I'll put minus infinity to plus infinity, but that's making assumptions that we're in physical space. We could have our wave function in momentum space, and you'd be integrating over momentum from minus infinity to plus infinity, or Okay, so there's our answer. Good enough? Next question. What did Planck propose that would allow him to give a mathematical derivation? This is beginning the whole first quantum idea. What did he propose to allow him to give a mathematical derivation for black body radiation? Should be a space in there. Well, what did he propose? I didn't. Oh. He proposed that if the energy at a given frequency was equal to an integer multiple of a constant times that frequency, and of course, I'm pretty sure one of you mentioned that this is the way you're more comfortable seeing it. Nu for frequency instead of F for frequency. If the energy at a given frequency is an integer multiple of h, the self-named Planck's constant, times frequency, then with only specific amounts of energy for each different frequency, using statistics, he could calculate and give exactly the equation that fit the black body radiation. So he proposed that, and it was important because that was, okay, 16 and 38 seconds. He proposed that, and so that was the first quantum hypothesis. Now, I say it's the first quantum hypothesis. We should go back. I mean, Newton said that light was a particle, but he didn't say that the particle had to have only specific energies. So this here saying that it had only specific energies made it a first quantum hypothesis. Then we had Louis de Broglie, who made his statement that Erwin Schrödinger took hold of. What was Louis de Broglie's famous equation? Everything should be like light and have a dual nature with a wavelength of Planck's constant divided by momentum, which is the relationship for light. So that was, of course, Erwin Schrödinger gave a talk on that and then worked out the whole 9 yards based on the idea of, everything having a wavelength. Now, you don't see de Broglie's equation anywhere in Schrödinger's equation, but the idea is what prompted it. Okay, what quantum condition did Niels Bohr propose, right? So we're going through the history of quantum here. We had Planck first, then de Broglie, now Bohr. Actually, historically, Bohr is before de Broglie. This was like 1922 or 1923. This is like 1915. And this one here was, I think it's 1900, 1901, somewhere around there. Okay, so what quantum condition did Niels Bohr propose? That is a correct statement. This one here, I tried to make sure that we would choose a specific one. He had 4 things, right? So number 1 was is he correct? No. Number 2. What happened? I was looking down, so I didn't see it, but judging by the clock now, so that's just under 4 minutes. Electrons have stationary states, and they can't just continuously change energy. I don't have room to finish it out. Can't continuously change energy, so they can't give off radiation, because they should, if the planetary model is correct, they should just spiral into the core because they'd be giving off radiation because they're accelerating as they go around the circle. Number 3 is the payoff punch, the one we were looking for. By the way, was number 2 correct or incorrect? That's correct. Number 3, is that correct or incorrect? Also what? We had 1 correct and 1 incorrect, so I can't go what also means. Yeah, the angular momentum is quantized is correct. His quantization condition, incorrect. And then the last one was when changing stationary states, I'm just going to put delta E equals HF. It has to absorb a photon or emit a photon with energy exactly equal to the difference in energy between the stationary states. Is that one correct or incorrect? Okay, so he's batting 500. I mean, that's all-star material, right? If we're talking baseball. So Those were his conditions. The angular momentum being quantized was the specific property that he quantized. So that's why I had this statement here to make sure you would answer the one I wanted. Because the first one, or the second one as I have them listed here, is a quantum idea that you have only certain energies allowed. But the specific property that he quantized was angular momentum. And it turned out with the Bohr model and using standard classical physics, that quantum number n quantized everything. Angular momentum, energy, radius, velocity, all of those were quantized with the same quantum number. What was the failure? Why did we have to move on from his? Why did we decide he's wrong? Well, just the Bohr model in general. What evidence do we have that said this is wrong? You know, that's always correct. I mean, you can't fault a guy, can you? The primary reasons are which incorrect predictions, fine structure. When, you know, the Balmer series, the Lyman series, the Pasha series, the Bragg series, all of those were perfectly explained until you looked at them with too much detail. When you looked at them with too much detail, you see that they're off by just a little, and this is the one they noted, you have splitting of the lines that they call fine structure. And so that splitting of the lines couldn't be explained, so they had to come up with something new. And that brings us to the quantum model. And of course, if you put a magnetic field, you see the Zeeman effect, which is just a bigger example of the same thing. Another one I should point out, according to the Bohr model, your intensity for absorption emission should just be, you know, a continuous smooth function, not this one's bright, this one's faint, this one's bright, this one's faint, this one's faint, bright, bright, faint, you know. It should be a continuous function. That couldn't be explained with the Bohr model either. Okay, number 5. Why did Heisenberg develop his matrix method for quantum mechanics? I'm going to be lazy. Uh-oh, where's my eraser? Okay, this is crazy. There we go. It's like, why couldn't I erase? I was just missing where I had read. I just erased the answers on the test, so they're all there. He knew that it was impossible to determine the path of an electron in an atom, so he decided, forget it. Can't know it, not going to spend time on it. And so he said, let's just focus on the things that are observable, the things we can determine, and try to categorize them and figure out what patterns involved. And then in trying to recognize the patterns, develop the matrix method. Okay, now, small problems. By now, are you guys appreciating my sense of humor with the quote around small? So here we only had 4 possible positions. And we have frequencies for each one. And we're going to make a real-life example of quantum physics calculations. So this is just to make sure that we understand what the calculations would correspond to in a real-life type situation. So find the expectation value for the position in this system along with standard deviation of position. Oops. I didn't want to erase all of that. There we go. I have the eraser tool selected. That's why that happened, in case you're wondering. How do we calculate the expectation value?
Wasn't it position times frequency divided by or
Okay, so here was our definition for expectation value. Well, now we're going to be doing something that's more fundamental. I don't have a wave function. I can't do integral psi star x psi dx because I don't have a wave function. I don't have a continuous thing. But what I can do is I can do the integral of probability of x times x dx. That's what this expectation value integral actually means. It's the integral of the probability of each value over all space. But of course, this is discrete. So in the discrete limit, summation or integral sign means summation. The sum over I, and I is going to start at 1 and end at 4, of x sub I, p sub I. Notice I even added them for you so you know that there's 1,000 times. You didn't have to add up 3, 4, 2, and 1. I was killing it for you. So position value 1 is 1. Probability 1 . There's my first one. There's my second one. There's my third one. Ah! I know I sound halfway like Chewbacca here. My final one. And then you had to add these babies up. So 3 plus 8 plus 6 plus 4. 21. And I had units there actually. So all of these were units, meters. So there's the expectation value, right? What do I need to do to find the standard deviation? I don't remember which way it is actually. That's why I give you equation sheets. Yeah, figure out which one is real and which one's imaginary. It's the real one. So that means you had to calculate x squared expectation value, which is I'm shortening things up now. So that's 4 times 4 is, wow. Yes, 4 times 4 is 16. Where did the 2 come from? 9 times 2 is 18. Does that look right? Chris, you're a math major. I always look at you. Okay. And I told Chris you wouldn't need calculators, and then I was like, oh, wait a minute. You got to do 2.1 squared. You have to do 2.1 squared in your head, which isn't that hard. That'd be 4.4. Now is the harder one. Not 1, 0. Zero 0.09 something, right? Or no, 0.9 something. Darn it. Zero 0.9 what? Okay, so that was just, I mean, it was practical work. At this point, hopefully that's pretty basic to you. Okay, what is the value for the constant A? Assume A is real. You know what I'm going to have to do? Erase this stuff because there's got to be something that I'm missing here. I'm not sure what happened here. This can't be what it said for your copy, right? It had to say for particle in a box. I totally didn't notice this morning when I was making this, or this morning, it was last night, but. Okay, so I've erased everything, but now we can see what it was. You had psi is equal to A given that psi is that, what is A? So something's happened. I can't hear you guys. I don't know if it's my ears or you're not speaking very loud or what. What's the method? Where are you going? Can you hear me now? Okay. I can just barely hear you. I'll turn my volume up some more. I cranked it up already, but.
He's going to mess with that volume. Our microphones.
Well, I've turned it up now, so I do hear you. Well, let's not worry about it, Chris. I've cranked it up here, so it'll be okay. It's just something happened to make you guys get softer for some reason. Yeah. It's somebody next door who's controlling things. Let's play with this. Okay, so what's the method to find the value of A in this? I mean, what's the name for it and what's the mechanism?
Normalization.
Okay. Normalization.
Yeah. So it's the integral overall space of the mod squared form.
Perfect. And so then we just put, yes, 0 to L because we're in a box. He said overall space, and in this case, it would be integral of 0 from minus infinity to 0, this integral from 0 to L, and then integral of 0 from L to infinity, if you wanted to be all kinds of anal.
I wasn't, when I took the test, I wasn't thinking clearly, okay?
What? I don't remember what you put on that test now, Chris. I'm not making any specific comments.
My integral of space did not have an L and 0 in it. That's something else.
Oh. Which makes it so you can't get a value. Okay. So when you do this integral, A star times A is A mod squared. Sine squared of 4 pi over Lx. If you graph that, yeah. If you graph that, you're going through 4 complete cycles of a sinusoid that has as its maximum here the A mod squared, and its minimum 0. And so just based on symmetry, what's the average value?
In the middle.
In the middle. So just based on symmetry, we can say that this integral is that. And there's one more thing that we have to keep in mind. The average is that when you're doing the integral, you're multiplying by the delta L, so it's times L. Or to make it complete with my graphical integration, average value of 1/2 times width L. Height times width.
Yeah.
And so then we get A mod squared is equal to L over 2. A is equal to square root L over 2 is one of the possible answers. Name a second possible answer.
Minus square root of L over 2.
Okay. Name a third possible answer. Here's the entire family of answers. For all, I should say all real phi. So you have an infinite number of possible answers. You could have any phase, because remember, e to the I phi is equal to cosine phi plus I sine phi. It has a magnitude of 1, and it can be any angle in the complex plane. Because of the mod squared, e to the I phi mod squared is just 1. And so that covers all of your possible answers. But of course, for the test problem, we weren't looking for all of the possible answers. Assume A is real. I should have said and positive, because you still have 2 correct answers. And of course, I would have given you credit with either of the correct answers. But if I said A and positive, then there'd only be 1 correct answer. Okay. Next problem. What is the expectation value for position for this same? Oh, I know what it is. Nope. Yes. Refer to the following for the rest of the questions. I erased it with everything else. I'm going to go back and erase it again, but that's That's what we were missing. We didn't have a problem with the test, thank goodness.
Yeah.
I know it's a little late to figure it out now. So how do I find the expectation value for position? Integral from what limits, Chris?
Yeah, 0 to L. X, psi, x, c.
Yeah, I'm looking that way. That's what I just did. Okay, now adding the x makes it all the less fun. So here's the integral without limits. And from the integral table, it gives us this thingy-bob. And so cosine 2x going from 0 to L is going to be going from 0 to 4 pi for the angle. And so that's an integer number of cycles for cosine, hence it's 0.
Yeah.
Sine, once again, actually that's got it, has a 2, so it's going from 0 to 8 pi. I missed that. Sine going from 0 to 8 pi, that's an integer number of cycles. Again, that's going to be 0. So when I put in the limits, those just give me zeros. And so I can short circuit this to be now, of course, in your solution, you have to write all the words that I said. Right? You can't just say, and then magic appears and these two go to 0 and okay, so that was easy. Draw a graph of the probability density from 0 to L and identify the locations where the particle is most likely to be found, as well as the expectation value. That looks exactly like this. Well, remember it's squared, so sine squared, which is why you have 4 cycles. I'd actually already drawn that function right here. Oh, did you say all positive?
No, I say it was all positive because there's going to be your probability density is going to be positive.
Okay, so here you see the 4 locations where 4 locations where it's most probable. The peaks, easy to identify. And then there's the expectation value right there.
Easy.
And you have the case that you know now exists. There's 0 chance of it ever being at the expectation value, which tells you that it's not the most likely position. All right, what is the wave function of the momentum operator? Or is this a wave function of the momentum operator? We can answer now differently. We could say, we could say that. Right, because that's the importance of the commutator, right? It tells you, hey, they share the same eigenstates. That means you can know both values at the same time, which means you have no uncertainty relation, right? Lots of different statements that all tie into this. Well, at that point, we only had one way of doing it. And the one way of doing it was to say, does P operator acting on psi equal a P value times the same self-same function psi? So we had minus I h bar d dx of psi is equal to And you're like, what? That ain't psi. Right, so that's the only way you had to answer then. Not a hard way, but now we're more sophisticated. We have more understanding. And then we had a bonus question. What's the kinetic energy for this particle?
I was gonna say,
Let's make it exact. And so we see, aha, we had success. Now, I had a failure on my selecting the box as well as apparently choosing my color. Yeah, that's right. So they have the same psi there. So we say, woo, this is an eigenstate of the kinetic energy operator with kinetic energy apparently equal to yeah. All right. We are out of time now, according to that clock. Your clock is exactly the same style as my clock, by the way. I don't know if you can. Yeah. Doesn't mean that is yours Timex?
It doesn't have any.
Mine bottom center says Timex. That's why I was asking.
We don't have a lower one.
So yours is a cheap knockoff. Mine must be the one keeping correct time.
Oh, probably. I do have a question about the homework.
Yeah.
If you have a quick second.
I got time for you.
Cool. So on the second or third question, I think it's the third because there's four. Yeah. So for 3C, are we doing the same thing as on the previous homework, where we're taking a combination of the two?
What you're going to do here, I have to think through the whole problem. I can't answer without thinking about it carefully. I do remember one thing: the probability of being in the probability of triplet is equal to 1 minus the probability of being in the singlet. Because you can do the singlet calculation, the probability of being the singlet in one step, whereas probability of being triplet, you have 3 different to consider. And so probability of being the singlet is going to be that mod squared would be the probability of being the singlet state.
And then are you using side 1 and side 2? Or?
Your state here So this is the state for electron 1. This is the state for electron 2. And because it tells us that it's in, the 2 electrons are in a spin singlet state, then we know that our state is that. And so we're going to take the chi plus means, I prefer to write them like this. Electron 1 is in a state described by this, and electron 2 is a state. So then I'm going to take this here is my bra, and my ket is this. So this state multiplied by this state. Which gives you a nice complicated set of terms.